Hey everyone, in this video we will talk about sequences and their limits. Alright, so what is a sequence? So this is just going to be a bunch of numbers that we write out, forever here. And usually we have a pattern for our terms in some way. So as we go on down the line, we'll say like this here, this AK is called the kth term of the sequence, right? So we'd have first term, second term, third term. And then to talk about an arbitrary term, we would say the kth term in position K. And the way we would denote this is we'd use these curly braces and write AK from K equals 1 to infinity. So this would exactly correspond to what I have written above. Okay? So let's look at some examples now. Okay, so let's look at these two. So the first one, I'll have the kth term be 1 minus 1 over k. And so if I look at this as k goes from 1 to infinity, then I start my list with a1, right? So a1 is 1 minus 1 over 1, which is 0. a2 then is 1 minus 1 over 2, which is 1/2. Next one would be 1 minus 1/3, which is 2/3. And so on. And so you get like 0, 1/2, 2/3, 3/4, and you keep going, right? And so another way to view this, right, if you had a common denominator there, then this is exactly k minus 1 over k, if you want. And one thing to notice is that as you go off to infinity here, these terms are approaching 1, right? So we'll talk about limits of sequences here more rigorously in a second. This is just kind of something to notice. So for the second example, right, so we have, again, k equals 1 to infinity, and so 1 over k squared, we start with 1, and then it's 1 over 2 squared, 1/4, 1 over 3 squared, 1/9, 1/16, and again, you just keep going forever. And what do we notice these terms going to? So we keep dividing by something bigger and bigger, and eventually we're going to get really, really close to 0. So, these are somewhat like limits for our usual functions, but notice the difference here is that these are discrete. So let's look at this on a graph. Okay, so let's take a graphical look at this 1 over k squared sequence. So our first term, right, is going to be 1 over 1. And so it's up here. And then next we have 1 over 2 squared, so 1/4 down here. Then 1/9, which is pretty small, so maybe down here. 1/16, we're getting really small, right? 1/25, that's 0.04. And this is going to keep happening, right? We're going to get closer and closer to 0. But the key is with this graph, we only have these individual points spaced out one at a time. Whereas 1 over x squared, right, would be the thing in the blue kind of connecting them. This would be 1 over x squared. And so this is the difference between a sequence and the function, and why limits could be maybe slightly different. But we actually have a nice result about how the limits will correspond that we'll talk about soon. All right, let's start with a very ambiguous definition here. So what is a limit? So we say that the limit of a sequence, so the limit as k approaches infinity of ak, the terms of the sequence, is L if the kth term is as close to L as we want, so long as k is big enough. So it's a lot of ambiguity there maybe. So let's take a look at this again. So what you want to start with, right, so maybe we have 1 here, and then we get down here and we say, you know what? I know that this 1 over k squared guy should be going to 0. That's what it looks like to me. How do I prove it? Well, I'm going to take this arbitrary error, say it's 0.1 in this case, right? So I make my little band of 0.1 width in either direction. And then I look at my points. I'm like, okay, so I start at 1, and then I go to 1/4, and then I go to 1/9, which is just above this. And then I get to 1/16, right? And then I'm within here. And for the rest of time, I will have things that are really close to 0, closer than 0.1. And so the point is here, once I cross this threshold of k equals 3, once I get past 3, I will always be within 0.1 of my L, right? Where L is 0 here. And so that's the idea. Pick your error bound. Eventually, once you cross some threshold, you will be within that error bound. That's what it means to have this limit. Okay, so let's look at a weird example. So this is kind of a cool one. So we have sine of pi k over 2 over k. So let's just go ahead and graph it. So this one, sine is going to change sign here. So notice that this keeps rotating from pi over 2 to pi, to 3 pi over 2, to 2 pi. And then you go back around. So we're hitting kind of the 4 90-degree things on the unit circle. So what we start out with, right, is 1. So sine of pi over 2 is 1 over 1 is 1. And then we go to sine of pi, but that's 0. And then we go to sine of 3 pi over 2, which is -1, but then we're at 3, so -1/3. 0 again for sine of 2 pi. Then we go to 1/5 because we're back at sine of pi over 2. 0, -1/7, and you can kind of see the pattern, right? Every other one is 0, and then the other ones we keep switching sides, and we add 2 to the denominator. So what does this look like pictorially? Well, you're up at like 1, then you go to 0, then you go to something not too big, back to 0, then to something closer to 0, but still not 0, and you keep getting closer to the x-axis, and you're on either side of it the whole time, right? And so the idea again is no matter where you draw your line, eventually you will hit a threshold where you're within, right? Everything from now on to the right is going to be within my error bounds. And so here we would say the limit of the AKs is 0 as k approaches infinity. So for your first exercise, I want you to find the limits of these two sequences. So the first one, so this -1 to the k, you should figure out what that does. This is something that will commonly show up in sequences. And so one of them will have it over k squared and the other one just times k. So here's an important theorem that we can use and is somewhat seen in our previous problems. So if f is a function that is defined for all x bigger than or equal to 1, and its limit as you go to infinity is L, then if you just take the points at integers for this function and take that sequence, then that sequence will also approach L, right? So basically what we do is, we saw that one with sine where we keep bouncing back and forth and we like cross 0. And I realized that this is all in black and that was a terrible idea. Then okay, it seems like this is going to 0. Well, sure, I can try to use this like I see that the error bound could be made, whatever. Sure. Or I can fill this in and say, hey, what happens to sine of pi over 2 or pi x over 2 over x as x goes to infinity, and use the squeeze theorem, right? Because we know that this top is always between -1 and 1, and the bottom is going to infinity. So this guy is 0 with the whole function. Thus, these points, now in blue, must also go to 0. So why is this theorem nice? Well, we've done a lot of work with limits of functions, right? We haven't done as much work with limits of sequences. Well, now we can leverage that work that we've done for functions, so we can use things like L'Hopital's rule to do limits of sequences. So let's consider, for example, this function. Or this sequence, sorry. We have n plus ln of n over n squared. And so instead, we're like, okay, that's the sequence. Let's look at the function itself. So let's look at this for all x greater than or equal to 1. It is defined for all of them, so this makes sense. Now what happens? Well, I get infinity over infinity here, right, if I plug it in. So I use L'Hopital's rule. And when I do L'Hopital's, I get the limit as x approaches infinity of 1 plus 1 over x over 2x. This top is going to 1, right? Because 1 over x goes to 0. The bottom is going to infinity, so this guy is going to go to 0. And once I know that, by a theorem, this must also approach 0. All right, so for your second exercise, this one's going to be a little bit challenging. I want you to use L'Hopital's rule to find this limit. And remember, if we have something like this, where you have like 1 to the infinity, it is an indeterminate form, and we can use the e to the natural log trick. All right, thank you for watching.